We will analyze now the last function of this list. There's one, right? Okay, first observation we're going to make is that this function is odd. It's an odd function because so is the arctangent, right? And the arcsine. Both are odd functions, and well, the argument of the arctangent is just x, but the argument of the arcsine is this, which is a function that changes sign when x changes sign because of this x here and because the denominator only contains x squared. All right, so this function is odd, which means that we need only focus on the positive side and we will have everything. About the domain of the function, the arctangent is well defined for any argument that you put here. The arctangent is just a function that goes like this from minus pi half to pi half as the argument goes from minus infinity to plus infinity. It's well defined everywhere. The arcsine is only well defined if the argument is between minus 1 and 1. Okay, so let's see. Let's see where is this argument here, right? So the point is 2x over 1 plus x squared must be smaller than or equal to 1. Well, in absolute value, right? In absolute value has to be smaller than or equal to 1. Okay? So it has to be between minus 1 and 1. Right. Well, to figure out what this is, we can multiply by the denominator, which is always positive. So we have 2, the absolute value of x is smaller than 1 plus x squared, right? And this, if we put this on the other side, what we have is 1 minus 2 absolute value of x plus x squared larger than or equal to 0, right? We put it here, so this expression has to be larger than or equal to 0. But this expression here is just a perfect square. It's the absolute value of x minus 1 squared, right? You have the first term is the absolute value squared, which is x squared, then minus twice the product, and 1. And that is larger than or equal to 0 always. So actually, this and this are equivalent, which means that the region where this is true is the region where this is true, which is everywhere. So this argument is always between minus 1 and 1. So the function is defined everywhere, which means the domain of the function is R. All right, so we don't have to worry about this function, about evaluating this function. There are no vertical asymptotes of this function, right? On the other hand, because for a vertical asymptote, the function has to be divergent at some point, right? And it is not, okay? All right. Next thing we should analyze is what happens at the infinities. So when x goes to, let's say first infinity. The first part is clear. When x goes to infinity, the arctangent goes to pi half. So the first part is pi, goes to pi. So what happens to this? Well, the argument when x goes to infinity, the argument goes to 0. The arcsine goes to 0. So this goes to pi, right? Okay, what happens when x goes to minus infinity? Well, the function then this term here goes to minus pi half, so it goes to minus pi. And the same thing with the other argument, the denominator. The degree of the denominator is smaller than this one, so this goes to 0 when x goes to minus infinity. The arcsine of 0 is 0, so minus pi is the limit. So you have two horizontal asymptotes. One is when x goes to infinity and is pi. The other one is when x goes to infinity, to minus infinity and is negative pi, right? So no vertical asymptotes, but two horizontal asymptotes. Well, we will see later that there are more than that. Okay, the next thing to do is to calculate the derivatives here. All right, the derivatives are, oh, by the way, this is consistent with the fact that the function is odd. So if it goes to plus infinity to plus pi at infinity, it has to go to minus pi at minus infinity. The function is also continuous everywhere, right? Because so are these functions, and this is a rational function with a denominator that is never 0, so it's continuous. that means that at 0, the function must be 0 because it's odd, right? And it's true because if you make x equal to 0 here, this is 0 and this is 0, right? Okay, so we have a lot of information. The next we need to do is to calculate the derivatives of this function. So if we calculate f prime, what we have is twice 1 plus x squared in the denominator, and then we have 1 over the square root of 1 minus 2x over 1 plus x squared, and then we multiply this by the derivative of that, which is 2 times 1 plus x squared minus 4x squared, so it's 2x times the derivative of this, which is 2x as well, and in the denominator we have the square of this, 1 plus x squared. Right, we have here 2 over 1 plus x squared, and we're going to manipulate this a little bit. First of all, we're going to reduce this to a common fraction, right? And since, well, if you reduce this to a common fraction, what you get is 1 plus x squared minus 4x squared. Well, or just let me put it as it is now, 2x squared, right? And in the denominator you have 1 plus x squared. All right, everything is inside the square root, so the denominator, which goes up here, is just the square root of this square, which is 1 plus x squared, because 1 plus x squared is positive. So we have here 1 plus x squared. And in the denominator, we have the square root of this expression. But this expression here is the difference of two squares. So this is the difference times the sum. And the difference times the sum means that this is, the difference is x squared minus 2x plus 1. And the sum is x squared plus 2x plus 1. One of these is just x squared minus 1. X minus 1 squared. X minus 1 squared. The other one is x plus 1 squared. But when you multiply x minus 1 squared times x plus 1 squared, you're multiplying the difference and the sum. So you have the difference of the squares squared. So that is what you have. You have the square root of this, okay? But the square root of this is, of course, the absolute value of x squared minus 1, because this can be positive or negative, right? All right. Now, in the numerator here, what we have is 2 minus 2x squared, okay? Which, factoring out the 2, we can better write as 2 times 1 minus x squared, okay? And in the denominator here, we have 1 plus x squared. All right, now you take this, and it cancels with that, right? So we have, wait a moment. Okay, so we simplify this expression, and then we have this. We have 2 over 1 plus x squared plus, and here we have 2 over 1 plus x squared. So let me just put a bracket and common factor. And here we have 1 minus x squared divided by the absolute value of 1 minus x squared. Okay, doesn't matter if you write the absolute value of x squared minus 1 or of 1 minus x squared. Of course, the sign doesn't matter inside an absolute value. All right, so the result of this depends on whether x squared is smaller than 1 or larger than 1, right? So we have the following result for f prime. If x squared is smaller than 1, right, which means the absolute value of x is smaller than 1, then this is positive and is identical to this one, right? So this is just 2, so what we have is 4 over 1 plus x squared. If on the other hand, x is, well actually this is also, well, no. If on the other hand this is larger than 1, then this is negative, but this is positive, it has the same value, but it's positive, right? So 1 minus 1 is equal to 0. So what we have here is equal to 0. Okay? So the derivative is discontinuous because when we are in this region and we approach x equal to 1, well, absolute value of x equal to 1, then this goes to 2. However, here, on the other side, the function, the derivative is 0. So the derivative is discontinuous at the point 1, okay? Right. But on the other hand, the derivative is always positive or 0. So in this region it's always positive, in this region it's always 0. The derivative being 0 means that the function is constant in this region, right? And remember, the asymptotic behavior of the function when x goes to plus infinity or minus infinity, which is obviously in this region here, is pi and minus pi, which means that this function is constant equal to pi. If so, f is equal to pi in the interval 1 infinity, and f is equal to minus pi in minus infinity 1. All right. But the function is continuous, so we could include also the value 1. Doesn't matter, right? Sorry, this is minus 1. Minus infinity minus 1. Okay. So we have everything that we need to plot this function. Except perhaps if we want to calculate the concavity, which is very easy because, well, the concavity of this region is a constant. Is neither concave or convex, right? And in this region here is very easy because if we calculate the second derivative here, what we get is minus 8x over 1 plus x squared, right? By applying the chain rule. So it changes sign. So it is positive when x is negative and is negative when x is positive. So it has the opposite sign to x. So that means this is positive is convex, right? So it's convex in the negative side, concave in the positive side. Okay, we have all the information to plot the function. So this plot is like this. Okay, you see? The function is always increasing or constant, and it's continuous. But you see the symmetry is an odd function, so you can see that is the mirror image of this with the opposite sign, right? So here is pi, here is minus pi. In the region minus 1, 1, it is increasing, okay, it goes through 0. It is convex here and concave here. So there you go. Actually, the slope here, you know, is 2. So this tangent has a slope 2. This tangent here has a slope 2 as well, right? So there's a discontinuity on the slope here. So that's why you have this cusp, these two cusps. Okay, there you go.